Hello everybody, this is again the MATLAB and Simulink Racing Lounge. In today's episode we are going to talk about CAN communication with your control units using the Vehicle Networks Toolbox. And again, for that episode I'm really glad to have a colleague on board. Hello Jeremy.
Hello.
Hey, Jeremy is sitting in the Michigan office of MathWorks. And Jeremy, could you please introduce yourself briefly, why you are the right guy to do the episode with?
Yeah, my name is Jeremy Pyle, and I've been with MathWorks a little over 8 years. I'm the development team lead for the Vehicle Network Toolbox product, so the lead developer for that device. Prior to coming to MathWorks, I spent the bulk of my career working in automotive electronics and focused on vehicle network technology.
Perfect. So actually what we have today is a software developer sharing his knowledge. Perfect. And what are we going to do? Well, we will introduce you to the features of the Vehicle Networks Toolbox, and for sure we will talk about the capabilities in a software demo. I think before actually moving to the software demo, we should lose some words on the motivation behind. I think that's an image that is pretty common. So before the race or before an actual dynamic event, you have to tweak and tune something. And if you have access to your vehicle network using a certain toolbox, well, you can, do the right thing. And essentially the Vehicle Network Toolbox is, let's say, a window into the operation of your vehicle. Jeremy, did I introduce the main motivation of the Vehicle Networks Toolbox in a right way?
Yep, that's absolutely correct. Yep, so the value really here is that in-vehicle networking is the backbone of the electronic operation of a car. A vehicle is a distributed embedded system with features operating from module to module for all kinds of different activities, from driving the vehicle to body electronics and so on. Within that realm, controller area network, or CAN, is the most common protocol that we see, and so that's what we're going to focus on here today. But that connectivity tying into that network lets us inspect, test, and validate the operation of the vehicle by looking at all of the messaging and activity that's going on there. And with the Vehicle Network Toolbox, we have a direct connection from MATLAB and Simulink to accomplish that.
Okay. Well, this totally makes sense to me, but when it comes to the details, how do I actually connect to my vehicle network?
So for connectivity, VNT connects through third-party devices to physical networks. We support devices from Vector, Kvasir, Peak System, and National Instruments, and they come in a variety of form factors. Usually we see people using USB devices, but they do come in other form factors as well. Our toolbox connects to that device through an API that the vendor provides and allows us that direct access to the external CAN bus. The nice thing about having VNT is that despite all of the devices that we support and all the vendors that we support, the toolbox provides a common API. So the MATLAB function and the blocks that we use are the same regardless of which device you actually take advantage of.
So I don't have to take care of, putting my commands in a different format. It's always the same interface to the third-party tools, or third-party hardware in that case.
And in terms of getting started with these devices, a great resource is our hardware support packages. The hardware support packages for VNT allow you to very quickly and easily install the free drivers available from the vendors for those devices and configure your system for operation in just a few clicks.
Okay, so before jumping into the software demonstration, let me ask the question, what are the prerequisites for the Vehicle Networks Toolbox? So, if you interface to MATLAB and Simulink, these tools are required somehow, but is there anything else our viewers might need to get started with that?
We need a device and we need drivers for that device. So that could be a physical device, or in some cases as well, the vendors provide virtual hardware. We'll get into that in a little bit more detail to come. But once you have the device and you have the drivers configured through those support packages, you're good to go.
Perfect. No, makes sense to me. So really looking forward to the software demonstration where we are talking about the interfaces to both MATLAB and Simulink.
All right. So let's jump right in here. So what we're going to do essentially in the overview of this demo is send some CAN data from MATLAB into a Simulink model that we'll build and then round trip that data basically back to us and visualize it along the way. So when we get started with our interfacing to a CAN network, the usual place that we begin is with a DVC file. Those database files contain definition of all of the messages and signals that are being transmitted around on the network. You can kind of think about your CAN data in two ways. One is the raw information with message IDs, and the raw data being transmitted, or you can think about it at an application level where you have signals that are unpacked and decoded from that raw data, and the database contains all those definitions.
Okay.
What we can do in the toolbox is we can access these DBC files and essentially use them to be able to interface to the network at that application level.
Okay.
So what I've done here is I've executed our CAN database function, and I've specified the DBC file that we want to use. This is a demonstration file that we set up for today. And in return, I get an object at the command line, which gives me access to that database file. We have methods and ways to pull information from the DBC file and use it.
Okay, perfect. Let me ask a question. This DBC file format, is it also part of the CAN protocol?
No, no. DBC file format was created by Vector and kind of became a de facto industry standard in automotive, but it's not specified in the protocol.
Okay, got it.
In terms of the messages that we're actually going to send back and forth here, we had pre-configured some messages prior to the demo. But what I have here, what I loaded from a MATLAB file essentially, is those messages. I have an array of 500 CAN messages, and if I take a look at these, we can see that they have properties that are akin to all of the base elements of a CAN frame. I have a message ID. I have the database that I'm using attached to this message, and you can see its name is available there, as well as its data. And we also have direct access to the signals contained.
Signals itself. Okay.
These I just loaded, but if I actually wanted to create one of these, I can do that very easily. We have a CAN message function that allows us to specify a database file to use, and then we just basically give it the name of that message, and I can create a new instance of one of these CAN message objects.
Got it.
So that data is ready to go. The other thing that we need to set up and basically get ready here is our hardware. CAN hardware info is our hardware discovery function. It allows us to enumerate all of the devices that MATLAB sees available on the system. So that's everything that's plugged in and has the drivers correctly configured. I've got several here, some devices from Vector, some devices from Kvaser as well. But for today's demonstration, we're going to use the virtual channels provided with the Vector drivers. The virtual channels are really beneficial because they let us essentially simulate CAN connectivity or CAN messaging. They don't go to the level of detail of the electrical characteristics of the network, but generally speaking, where our users are concerned, where they're operating is at the application level. They don't care about the details of the protocol and the implementation of the messages. They just want to get their data. They need to know their vehicle RPM, their vehicle speed, and the hundreds of other parameters that they can get off that bus. And they want them as real signals and engineering units that they can use in their application.
Well, and I also can imagine that in industry, the workflow, the current or the classical workflow is to work with virtual hardware devices, because you cannot go to the real car anytime you want to check whether a development step has been successful.
Yeah, absolutely. Our users often start in the virtual realm, using Simulink and MATLAB and virtual channels to do their initial development, prove out their concepts, set up their test environments. And then it's very easy to change from a virtual environment to the physical environment and a real device, and come back and iterate as well as you go from vehicle to simulation, vehicle to simulation.
Okay. So, well, as a user, I should not care about whether I'm working with a virtual vector or a real-world vector, so the interface here is pretty much seamless.
Absolutely.
Okay.
So what I'm going to create here on the command line is a channel object that would represent a connection to a device in MATLAB. For that, we have a CAN channel function, and I specify the name of the vendor, the name of the device, and the channel number that I want to connect to. Okay. And I get back a new command line object, a CAN channel object.
But it says still offline?
Still offline, yep. It comes up, it's built and it's in a configurable state. So if I needed to do things like change my bus speed or maybe set up some other parameters or options, I can do that. But we're going to leave that channel dormant for the time being. We're going to go over to Simulink and start building the model that we're going to interface this channel to.
Okay, perfect.
So I have the Simulink library browser already open. We can see there's a vehicle network toolbox entry within there. two libraries under VNT, one for CAN communication, one for XCP. CAN communication is where all the basic blocks are for general messaging connectivity, and XCP is blocks specific to that calibration protocol which runs on top of a CAN bus.
Okay. So could you name a use case for the XCP protocol? So just as an example, well, where can it be meaningful to have that on board?
So XCP comes into play if you have XCP server code essentially implemented in the modules that are on your network. And what it does is it allows us to get deeper into almost like kind of a debug mode access to the module where we can read and write memory locations and get more to the internal operation of a module on the network. The CAN communication lets us only see the general messaging that's designed or defined for a network, but XCP lets us get into the internals of a specific module on the bus.
Perfect. Thanks.
So I'm going to go ahead and create a new model here. This will be our working model for the demonstration. And I'm going to start setting up some CAN connectivity. We start with our configuration block. That's the first thing that we need to have set up, which provides our base configuration for the channel that we're going to use. If I go ahead and open up this mask, the main thing that I need to select in here is what device do I want to...
Virtual channel,
do I want to connect with? So just like on the command line, we connected to that virtual channel, I'm going to do the same here. And the bus speed and the other parameters can all be left to defaults right now.
Okay. Yeah.
So the next thing that I need to add is a receive block. So we're going to be sending messages from MATLAB and receiving them in our Simulink model. So for that, I need CAN receive. If I open this mask, kind of similar configuration. Again, I need to choose which channel do I want this receive block to pull messages from. And then I'm going to go ahead and set up some filtering options so that only that one specific message that we'll be sending from MATLAB will pass through the receive block. This is a good thing to take advantage of. It makes the blocks run more efficiently, and you don't waste time processing other data that you might not be concerned with.
In general, it will completely avoid overflow and makes the access to the data more clear, right?
Yes. Yep.
Okay.
Absolutely. So that's our receive block, and we can see we have two outputs on the receive block. One is a function trigger, and the other is our CAN message data type that's specific to the VNT blocks.
So the first for triggering it, and the second one for sending the data.
Exactly. So I'm going to add a function triggered subsystem, and the reason that we kind of architect our blocks this way, and we recommend that our users do it so as well, is that in Simulink, Simulink is running at simulation speed, and on any given time step, when the CAN receive block executes, it's going to grab all the data, all the messages that were available since the last time it executed. Oftentimes, that's going to be more than one. And so we want to make sure that we send everything downstream to the model for processing, and that's why we use the function trigger. We get a function trigger for every message that the CAN receive block had available this time step.
Okay, that makes perfect sense.
So if we go into the function trigger, we can start setting things up in here. The next thing that we want to set is our unpack. And so what unpack does is it takes a CAN message as an input, and it allows us to basically decode that message and get the specific details out of it that we're concerned with. There's a few ways to configure it, but the most common and the one we're going to use today is the CANDB specified signals. And so we're going to load that database file that we referenced earlier.
Okay, let me ask a question at that point. So this database file, what actually does it contain? Does it contain the signals, or what is it?
The database file contains just the definitions of the messages and the signals contained within those messages on the network. There's no actual data, in that file. It's kind of a point of confusion oftentimes for our users to call it a database that doesn't have any data. But for our purposes and for our use, it's the definitions that are important. What is the decoding schema that we want to apply to the messages that are coming in off the bus and that we're sending out onto the bus?
Okay, just to be clear on that, the DBC file here contains all the definitions, can be seen as a configuration file, and where are actually our signals? So what signals do we send and where are they stored right now?
So in the database file here, we can see there's two messages defined. This message list shows me all of the message definitions that are in that DBC file. So we have two defined. We have an input message and an output message. And so I'm going to select this block to unpack the input message. That's the one that we're going to send from MATLAB. We can see down here, this is a table of all of the signals that are defined within that message. There's only one. It's an input signal, 16-bit unsigned integer. And what we're going to really send is a counter. It's going to count from 1 to 500.
1 to 500. Okay, perfect.
So if I look actually at the block here, when I opened the mask, we were outputting data. But when I loaded the database file and I configure it for the signals, that output's going to change.
Okay.
And now instead of outputting the raw data, it's outputting that actual decoded signal value for me.
Okay, perfect. So what comes in is a somehow crypted signal from the CAN system, and what comes out is a classical Simulink signal that I can do operations on.
Exactly. And just to show that we can affect some change on that when we send it back out on the network, go ahead and put a gain block in here and do a simple
just a very easy manipulation, just to demonstrate that.
Exactly. So then what we'll do is we'll take this modified output from the bus
and probably pack it again, right?
Pack it again, send it right back out. So for that, we need an unpack block. We'll see this is very similar to we need a pack block, which is very similar to the unpack block. I'm going to set it up for the database. I'm going to go ahead and load that database file. But instead of selecting input message, now I'm going to select output message. We can see that output message contains a single signal here, called the output signal. It's a 16-bit integer. It's a signed integer because we didn't.
In that case, it's signed. Yep. Perfect.
So we'll go ahead and put this here. Connect the gain block to the input of that pack block, and then the last thing we need in order to transmit that value out onto the
transmit block.
Transmit block. So we'll hook those up. Transmit block also needs to select the device through which we want to transmit. In that case, I'm going to choose the virtual device. And just a quick note about an interesting functionality here. This transmit messages periodically. That allows us to throttle the transmit according to a real-time periodic rate. We have the concept of simulation time running very fast, connecting through physical hardware to a real-time system externally. And in some cases, simulation time, given its speed, we don't want to transmit messages to a real-time system at simulation rate. So the transmit messages periodically allows us to throttle back our actual output to the physical system to a real-time data rate.
Okay. Well, this can be an important function, right?
Yeah, absolutely. The other thing I'm going to add in, just so that we can kind of visualize what's happening, is a display. So we'll take the output of our CAN signal, and then the value going back out onto the bus on a second display. So that's our model. That's what we're gonna run. We'll go ahead and set this to run indefinitely. And, if I go ahead and start it, we'll see that nothing happens initially. My displays are all 0. This function triggered subsystem is not actually executing because we don't have any input coming into the model yet.
Okay, so as soon as you call the function, the trigger will be on.
Yep, as soon as we start getting CAN data, we'll start getting those triggers.
Okay.
The other item or element of the toolbox that we want to show in conjunction with our MATLAB interface, our block set, is our CAN tool. This is a GUI tool used for visualizing CAN data on a bus.
Okay, perfect.
So I'm going to go ahead and set this up to also use the same virtual channel, and I'm going to set it up to use the same database file.
Okay.
And we'll go ahead and turn that on in the background. We'll go ahead and turn our model on in the background. And again, we can see nothing is happening. So let's generate some data and look at what happened. So again, we're going to use the CAN channel that we created previously. We need to go ahead and we need to put that channel online. We have a start function.
Okay.
So we can see our channel status went from offline to online. Now we're ready to send some data. And again, we have this array of messages, these 500 messages that we want to send out. The way that I'm going to do it is using a function called replay.
Okay.
Using the replay function, we can send an array of messages or a block of messages out at a certain time rate that's defined within those messages.
And you're sending that out periodically?
Well, not necessarily periodic, but more so according to the differentials of the timestamps. Each one of those 500 messages has a timestamp that we gave, and basically they're going at a 10 millisecond interval from 0 to to the 5 seconds. And when we do replay analyzes those timestamp values, and it sends each message out in succession according to the time difference from one to the next.
Got it.
So it's a feature that would be used primarily if we said we went out in vehicle and we took a log of message traffic, and then we wanted to bring it back to our desktop.
Okay. Yeah. Log and replay. Perfect.
Yep.
Makes sense.
Exactly. So when I go ahead and I execute this, oh, I'm sorry. I had the other item selected there.
No worries. Yeah, replay.
There we go. So we replay from our channel. Now we can see some activity. Our displays are counting up. The data coming in off the bus went from 0 to 500, and our gain was applied up to that negative 1,000. And we saw a lot of messages appearing in our CAN tool here. You can see we have the message identifiers, everything is timestamped, and we have the names showing up and the raw data. I'm going to go ahead and change the view on CAN tool. Instead of showing us everything in kind of a running list, this configuration option here for unique messages just shows us the latest instance of any given message. And so here we have our input message and our output message and the signals contained within. And so what this is showing us right now is the last instance of each of those messages where our data was 500 going in and our data was the negative 1,000 coming out.
Cool. Perfect. Makes sense. Well, although it has been a virtual demo, it's pretty impressive because, well, what I can see behind, I just replaced the virtual channels with actual hardware, and then I have access to, for example, control systems on my vehicle dynamics controls, everything. I just can, plug it onto my car's network and actually work with the signals. That's pretty impressive and, well, powerful feature.
Yeah, definitely so.
Yep.
And there's a whole lot more we can do with it as well. There's additional blocks specifically for doing replay logging within MATLAB. CAN tool lets you kind of configure the views and.
Okay. Well, this would have been my question at that point. So we have used a lot of commands. What is a good way to recap all those commands? If I want to get started with that.
So if you wanted to get an overview of the MATLAB function side of the toolbox, we can look at the help V&T for the product. This gives us a nice long list of all of our capability. Functions related to the CAN channel operation, messages, and our XCP function set as well. Okay,
perfect. So after each link, we will find specifications on the commands, what has to be specified, how to use that commands. Okay, perfect.
And then everything as well links to the doc. Very strong product doc for this.
Okay, well, just in case, this would have been my question as well. If I'm a former student team member and, I like that episode, I want to get started on that, should I just go to the documentation or do you have any other recommendation to get started?
No, I think the documentation is the perfect starting point. There's a complete function overview as well as a block overview and a couple dozen examples that walk through all the basics of the product from using the CAN channels to the messages, database files, both in MATLAB and in Simulink.
Okay. Well, for me, it seems that this is the right way or the right place to go in terms to get started with a Vehicle Networks toolbox. Well, at that point, Jeremy, thank you very much for that introduction. I think all of us, we could see the power behind the Vehicle Networks toolbox. And as we are now heading to the benefits, I think as you're the developer, you might also present the benefits of the Vehicle Networks toolbox just in summary.
Yeah, my pleasure. So the main benefit that we have here is that maintaining a single environment for all of your CAN network interfaces. Yeah. So if we're already using Simulink for our controls development, model-based development, we're already using MATLAB for some level of data analysis and visualization. Now we can bring that CAN data directly into either environment. We don't have to use third-party tools and deal with import and export capabilities and such. Everything is directly connected.
Well, and this is also the feedback that I get from Formula student teams. Basically, all teams are using MATLAB and or Simulink. And what I also see that CAN networks are pretty much a standard there. And I think the V&T at that point brings it all together.
Yeah. Another benefit here is the real-time communication. So whether we connect through MATLAB or we connect through Simulink, it gives us the opportunity to tie into the real-time external network, which is our module, our bench, or our vehicle. And MATLAB and Simulink are both perfectly capable of keeping up with the real-time operation of those networks.
Okay.
In addition, we have the connectivity for the virtual networks and virtual simulation, which gives us a whole range of in-the-loop style capabilities. We could simulate, say, a single module and connect that to an external network and run a model in the loop kind of approach. We could have a single physical module and run the rest of the bus or the rest of the system in simulation.
Virtual network, for example.
Yeah.
Okay.
So it's very flexible. And again, the development process is usually very iterative in that sense, where you start in the virtual, you migrate into the physical, and you iterate between the two.
Okay.
A couple other items listed here. Support for the CAN-DB database files. That's really the way, again, that most people work in industry with their CAN networks is using the descriptions contained in those database files to decode their messages and decode their signals and really operate at the application level. Log and replay available both in MATLAB and in Simulink, as well as the XCP support for the deeper access to modules on the bus.
Perfect. Well, that's we have get an overview of all that. But well, it's a really impressive tool. But we decided also to talk about current limitations. So well, just go ahead, Jeremy. I think it's also important to know about them.
Okay. One of the first limitations is with regards to our support for XCP. It's a relatively newer feature for the product, and XCP is a pretty broad, high-level application protocol. And so our implementation is really focused in on dynamic data acquisition and simulation for measurements. There's more that the protocol does, but our implementation is focused on that element of it, which really does satisfy the majority of the use cases for XCP.
Yeah, got it.
Another item to consider is with regards to the real-time operation. VNT is built as a host-side tool, so we're running on Windows, we're connecting through third-party hardware. It's not a true real-time environment because Windows itself is not a true real-time environment. We're not deploying VNT to any real-time targets. We have other products in the MathWorks portfolio that allow you to do that. So the benefit is that despite running on Windows and the timing characteristics that introduces for us, again, we do keep up with full bus speed, both in MATLAB and Simulink. And the other caveat is that any messages, any data coming in off of the bus is time-stamped in real time by the hardware at the very low level of the vendor drivers. So
we have even seen that for the virtual channel that there has been a timestamp column in the CAN tool.
Absolutely. So we'll never lose data, and all of our data will be properly time-stamped for real-time analytics. And the last item to note is just that VNT is limited to CAN. There are other network protocols used in automotive, LIN, FlexRay, and a handful of others, but our focus for the product has been on CAN because it really is such the normal standard for automotive in-vehicle networking.
Okay. Well, and today we basically have one key takeaway, and this is simply just use the Vehicle Networks toolbox. Just try it to connect your already available models in Simulink or your MATLAB scripts to your in-vehicle network. We have seen a tool that is capable of living in both worlds, and what we definitely suggest is to use it and try it out, and afterwards let us know how you succeeded, and we'll get back to that later. At that point, definitely want to say thank you very much, Jeremy. It was extraordinary. It was really interesting, and thanks for having you on board.
Thank you.
It was a pleasure. Perfect. Thanks a lot. And this really brings us to the end of today's session. As you know, if you want to find more videos of the Racing Lounge, just go to our Racing Lounge landing page under mathworks.com/racinglounge. If you want to get further information about your Formel Student competition, go to mathworks.com and FSG, for example, for Formel Student Germany. And as I've already said, we are really relying on your feedback. We are interested in hearing your comments and thoughts on that. Drop us an email, formulastudent@mathworks.com. And for those of you who are not aware that you can get MathWorks and MATLAB Simulink software for free during your competition, let me point you to our software offer. It's mathworks.com/FSG_software offer. And whenever you use our software, we would be really happy if you use our logo on your car and your reports. At that point, thanks for watching. Hope to see you next time. Bye-bye.